Hello, am I audible? Can anybody from audience, can anyone confirm, am I audible?
Yes, you are
Yes, you are
audible.
audible.
Yes, sir, you are audible.
Thank you, thank you.
Dr. Gupta, namaskar.
नमस्कार सर, नमस्कार.
PK Mishra this side. Namaskar.
Yes, sir. Namaskar.
You're fine, sir?
I'm fine.
Great, sir.
Good afternoon to all and welcome you on behalf of Institute for Steel Development and Growth. I, Dr. Siddharth Chauhan, extend a warm welcome to all of you to today's one-day webinar on Introduction to Prestressed Steel and Application. We are delighted to welcome participants from consulting organization, industry, academia, research institute, and the student community from across the country. Your enthusiastic participation reflects the growing interest in advanced steel technology and innovative structural engineering practices. Today's webinar focuses on one of the emerging areas of structural engineering, prestressed steel. Prestressing has been widely adopted in concrete structure. However, its application in steel structures offer opportunities for improving load carrying capacity, reducing deflection, optimizing material usage, and achieving economical and sustainable structural solution. This webinar aims to provide participants with understanding of fundamentals, behavior, concepts, and practical application of prestressed steel system. Before we begin, I would like to acknowledge and thank all our participants for taking time out of their busy schedule to join us today. It is now a privilege to introduce today's distinguished speaker, Professor Dr. L.M. Gupta, former professor at VNIT Nagpur, is a distinguished academician and expert in structural engineering with extensive experience in steel structure, prestressed systems, bridges, and rehabilitation of structure. He obtained his BE in Civil Engineering 1980, MTech in Structural Engineering 1983, and PhD in Structural Engineering 1991 from VRCE, now VNIT Nagpur. With a long academic career spanning over 3 decades at VNIT, he made significant contribution to teaching, research, and consultancy in structural engineering. His area of expertise Ma'am, please mute your mic, ma'am. His area of expertise includes steel structures, composite construction, and structural retrofitting, and has been actively involved in development of design methodologies and practical engineering solution. Professor Gupta has authored numerous research papers in reputed journals and conferences and has contributed to code development activities, including work related to pre-stressed steel bridges. A recipient of awards such as Best Teacher Award and recognition from Government of Maharashtra for bridge retrofitting projects, he continues to contribute to profession through academic, consultancy, and professional engagement. We are indeed privileged to have an eminent expert with us today. It is now privilege to invite our respected Director General INSDAG, Mr. P.K. Mishra sir, to address the gathering and share few words.
Thank you, Siddharth. Our gratitude to Dr. L.M. Gupta for having agreed to take this lecture, and we are really grateful for your association with this institute. For the information of the participants, this Institute for Steel Development and Growth, it is a not-for-profit organization which is promoted by Ministry of Steel, Government of India, along with main producers of steel, that is Tata Steel, JSW, SAIL, RINL, and ArcelorMittal. The very mandate of this institute is to promote usage of steel in construction. You all know, even though India is a large producer of steel, but our per capita consumption, our steel to cement ratio, they are much lower than world average. Because one of the major reasons we have discovered that the students who are coming out of the colleges after undergraduate courses or even postgraduate courses, they are not really exposed to steel contents in their curriculum. In fact, when I was discussing the subject with AICTE chairman Dr. Sitaram, who has now left that position, he himself is a eminent structural engineer. He was director of IIT Guwahati. He told in the country there are hardly 7 to 8, good professors who are familiar with steel in structural engineering, and we are fortunate to have one of them today as your speaker. Dr. Gupta is one of them. So when the knowledge, the steel content or knowledge and steel content in undergraduate courses is not there, how do you expect that the professionals or the students who are coming out to profession, how will they know about steel application? We are making various steps, and one of the steps that we have taken as an institute, we are making a lot of online training programs on contemporary topics. We are also organizing this kind of lecture sessions with the help of eminent experts or academicians like Professor Gupta. And we are trying to also make some kind of seminars, some kind of studies, some reports, whatever suggestions are coming from our patrons, we are trying to take up them. But I will request all the participants, please have a look at our website. We have got an online training calendar, and you'll find our intention is to make the calendar in such a way that if you follow these training programs, at least at the end of the year, you'll have some basic knowledge about steel in construction. That's their idea. Maybe some of the topics we can improve, or some of the topics we can add. And that we are doing with the help of all the academicians and experts from time to time. Your suggestions will also be helpful. But my request, please have a look at the website and see our activities, see our training calendars, the kind of steps that we are taking, and you may please give your suggestions also. You'll be happy to know that in the country today, uh, because there is no great journal on steel application today in the country, we are trying to make one journal with help of Professor L.M. Gupta and other eminent academicians from IIT Bombay, IIT Hyderabad, IIT Roorkee, and Dr. Gupta will be the head. And we are trying to launch that journal in next 3-4 months time, and you can find the topics will be again contemporary topics, and the our intention is to spread that awareness, technical as well as non-technical, among the users, among the readers, about steel applications. I once again thank Dr. Gupta for his support, and I also wish that more and more participants, more and more professionals will join INSTAG Forum to make this institute an institute of usefulness for the steel fraternity. Thank you.
Thank you, sir. Before we proceed to our technical session, I request all the participants to kindly follow a few housekeeping guidelines of today's webinar. Kindly keep your microphones muted throughout the webinar to avoid any background disturbances. Please keep your cameras switched off. Participants are requested to post their question in the chat box during the presentation. All queries will be addressed during the dedicated Q&A session at the end of the lecture. If any query remain unanswered due to time constraint, you may mail us at seminars@insdag.com. We will forward it to the speaker for an appropriate response. Now, I may request everyone to kindly mute your microphone. Without taking much of your valuable time, I now invite Professor Dr. L.M. Gupta to deliver his lecture on Introduction to Prestressed Steel and Application. Sir, may I request you to kindly deliver your presentation, sir?
Yeah, thank you, Siddharth, and thank you, Mr. Sir, for introducing the INSDAG, and as well as the Siddharth's introduction to myself. Now, first of all, I have to check whether I'm audible or not.
Sir, you are audible, sir. We can hear you.
Yeah. And the presentation is totally visible?
Yes, sir. Yes, sir.
Good.
It is visible.
Yeah. So there was a discussion with the INSDAG regarding this particular topic, and finally they has requested me to present this. The story of this particular topic is really very typical. When I completed my MTech in 1983, and when I started doing the registering for the PhD, my mentor, my professor, my guide, my teacher, my supervisor, Professor M. Basole, has given me this topic. Let us work on prestressed steel. And he's told me that you go to our market, that is called Sitabardi market, wherein you will get a book and buy that book, and from that book we can do the research work. I was really surprised that when the market I go to market, I got a book. The one person is selling the Russian books, and that was costing ₹12. So in 1984, I bought that book in ₹12, but I don't know, with the cost of book and the research work which we carried out, still not completed. Still, we can at least one decade we can also work. So much of the research material is available in that particular book, and the entire research work we did it with the help of that book, and that is the outcome of the 2 decades. Now that book is now Prestressed Load-Bearing Material by E. Belenia is published by Mir publisher Moscow, and that book helped us to produce 3 PhDs, 1 PhD of myself and 2 PhD of my faculty colleagues of my VRC, then VNIT, and 19 MTech projects, out of which I have reported only 13 because when I searched in my Almira, I am able to trace only the 13th hard volume copy of this particular project report. So I have listed here. So 3 PhDs and 13 MTech projects, out of which few MTech projects I am not able to cover because of the time requirement. And based on this PhD and MTech research work, I am presenting the total presentation of today. So I salute my all PhD and MTech students who has given me a innovative, a wonderful research work on prestressed steel, which is definitely very, very useful to our society. Now, people talk about these 3 things. People talk about the camber. It's an intentionally fabrication of upward curve so that the beam becomes straight after its own weight or maybe load applied. So what have camber helps? Camber helps only in serviceability. It doesn't help in the strength. Second is the lack of fit. When any structural component which is not able to assemble or a perfectly designed because of some slightly too long, too short or misaligned, the force of the member is forcible pull or push during construction. That creates a lack of fit. So lack of fit is nothing but the error. We can say that it's a question of error that may lead to some other extra forces in other members. But what is prestress? Prestress is a process which helps in strength as well as serviceability, both. So therefore, in our structure engineering, especially all structures has to have 3 S. One is strength, the second is serviceability, one third is stability. So what we are talking today on this prestressed steel, that we are talking about the strength, serviceability, and the stability thing. All 3 parts we are talking on this thing. So what is now the prestress? Application of predetermined concentric or static force to a steel member so that state of stress in the member resulting from this force and from any anticipated external loading will be restricted to certified limits. Or I can say that opposite stresses are introduced in the member before structure is actually used. The opposite stresses are introduced with the help of an external force which is controlled in magnitude as well as in direction to counteract the stresses which is going to develop because of the working load. So based on these definitions, the first part before going for the theory application, theory behavior, what are the various forms and shapes? You can see this is an axial tension member, consists of 2 channel back to back, which is prestressed by 4 strands used as a tension member. Then you can see various cross sections of the axial members. I can say axial members, which is mainly on the tension members, in which the strands or wires or prestressed material has been arranged in such a way that the concentric prestressing occur, because for every action there is a reaction, which is the principle which follow in our truss members, so which has been satisfied here. Then we can see the beams. A beam which is externally prestressed eccentrically in the bottom chord connected by a tension wire with the help of two brackets, and it is subjected to a uniform distributed load. So this wire, when it is pre-stressed, is introduced a compression in the member as well as a hogging movement developed in the member. So therefore, because of that application, the member initially deflect upward, and the stresses that are developed in the top and bottom fibers of opposite nature, as which is created with the help of the loading. Now we can see the different shapes. This is a plate girder with just wire connecting at the bottom. This is T, which is wire connected at the bottom. This is a box, which is wire inside. This is a box, which is wire outside. Now, so far what I shown is this is the straight wire, straight tendon. Now there are the provisions of, we can have a straight tendon from end to end. We can have partially wire in between these two brackets. We can have a curvilinear. We can have draft type. We can have V type, or we can have double tendons. So these are all possible ways of placing the tendons depending upon the type of structures we need and what type of we require. Then coming to the truss. Truss with straight tendon, truss with the straight one draft tendon, truss with the two draft tendons, and truss with two draft external tendons. Pratt type showing different single tendon with concentric piecing. Then variant type truss, again with single tendon, with one draft, with two drafts, or with external tendon. Then deck type. So these are mainly the trusses which are used for the transverse loading. Then we can see the trusses, arches and trusses, which has been stressed with the help of the tendons to reduce the deflection and increase the capacity. Now this entire study, which is being carried out in the following lines, that considering the theoretical problem, considering the effectiveness of the pre-stressing and geometrical optimizations, investigation is done with the help of the analytical process and also the experimental models. Then we have developed the calculations for strength, stability, and deformation capacity. And then finally, we need to have the performance in investigation. Now coming to the elastic behavior. There are certain assumptions in elastic theory. The plane sections remain plane before bending, after bending. They still follow the Hooke's law. The small creep under sustained loading is ignored. Material is homogeneous, isotropic. These are three very common assumptions applicable to all the theories which we referred. Then all fibers are free to expand and contract. But the number 5 is very important for this study. The analysis of pre-stressed steel beam is performed in the elastic range. The stresses at each section are linearly distributed across the section. The principle of supervision of forces and deformation and other general assumptions applicable to elastic analysis are valid. Because we are assuming that the wire which is stressed, tension is given, through brackets, it transports the force to the main member. Main member takes the compression to develop the equilibrium, and also generate the movement. So transfer of a force from one line to another line. So that is what the principle of supervision of the engineering mechanism is applicable, and which is assumed that it is 100% workable. If this is not workable, our theory doesn't valid. Means transfer of a force is very important. If I go back to this figure again, the transfer of force from this point. So the key factor of our study is this point, whether it may be here or it may be here. So assumption number 5, is to be taken care at all time. Now coming to the behavior, the elastic theory behavior, and because the study which we carried out before publication of the 2007 code, which is on limit state design, major studies are being done. So this entire elastic behavior is based on the 1984 code. So many of you are very much aware of the 1984 code, so they will be very helpful for you. Because what happens, we are not going in the non-linearity zone, we are only in the linear zone. There is no, the allowable stress is the fraction of the yield stress, and we are working on the factor of safety. So therefore, the entire study has been carried out. The entire project reports which I have shown of the MTech and the PhDs, which has started from 1984, and the last MTech project was 2020. Before I retired in 24. So last project, the Shubham Kharche has completed on the cold form section, application on cold form sections. That was the last project. Thereafter, I started my winding of the process. So therefore, no project I have allotted on that. So this total period, out of the maximum period, I was covered before the for publication of the 2007 code. But one or two projects, which is after 2007 code, where we have attempted to use the limit state design. So we are considering a simple beam with uniformly distributed load. There are three basic load systems we consider while doing the analysis. Those who are students, those are pursuing research, this particular point which I am putting are maybe very useful. One is the UDL, second is the central point load, third is the two uniform moment. Now out of these three, UDL maximum bending moment is only at center, then so slowly is gone decreasing towards support and becomes zero. Same story is that in the distribution is parabolic. Same story with point load, triangular distribution, maximum at center and reducing to zero. But the basic fundamental case, which is two uniform movement, wherein the movement is uniform in throughout all the cross sections. All cross section has to behave equally as same of the other one. So therefore, fundamentally, whenever you do any research, you should start with two uniform movements. Since here now, we are adding the tendon, so it's creating two uniform movements. So there, if you draw a Bending diagram, the Bending diagram will be between these 2 points of the bracket will be a rectangular block. And for UDL, it will be a parabola. And there will be one more extra diagram, that is the axial, say shear force diagram, bending diagram, and there will be axial force diagram. So therefore, there will be a bending stresses, there will be axial stresses. So our problem becomes indeterminate. Right. So considering this case of UDL, every structure have its own weight, so there will be stresses because of the self weight. There is stresses because of the self weight, which will create compression at top, bending compression at top, and bending tension at bottom. And when I pre-stress the tendon, P is the force, E is the eccentricity, as I shown here in the diagram. Then at transfer at centroid, it will be P plus PE. So because of P, there will be an entire cross section compression. Okay, and because of P, which is in hogging in nature, tension at top, compression at bottom. And if you add together, yeah, somebody asked something. Yes. Okay, so if I add for the pre-stressing case, it will sigma 1, sigma 2, plus sigma 2 minus sigma 1. And then if I summarize, then It will be summation of all the stresses at that junction, which is the case when there is no external load is acting. This is the case when starting. So what is happening in the starting case? In starting case, there is a stresses develop in the member. In the same time, there is a deflection in the member. Very unique case, wherein without load, external load, we are creating the stresses and deflection, upward deflection in the member, opposite to that of the load, stresses and deflection, which is coming because of the load. So here, what is point of consideration? Point of consideration during no load condition, no load, I put no load means there is no external load. No load condition, bottom fiber is in compression and top flange is in tension. So bottom flange, which is in compression, we have to consider, take care of is laterally restrained, laterally buckling of this member. Means the permissible stress at the bottom fiber, that is sigma BC or sigma BC, if I can say for bottom fiber, will be depends upon the lateral torsional buckling equation of 1984 code or maybe of 2007 code, which you deem fit. Because lateral torsional buckling phenomena is remain common, whether it's a 84 code or it's a plastic theory or it's a 2007 code. Which changes, which time with the time with changes, with the time it changes. When the load comes, the nature changes. That is one point. Second thing, the upward deflection. The upward deflection, it should not be too much of that. That is should be within the permissible limit of your code, or it should not damage the finishing or flooring of your structures. So this point has to be taken care. Now going further. So whatever I just discussed, the same thing has been in the bullet points. The stresses are developed, and what is happening here now? There is a final stress, which becomes the diagram of unsymmetric with neutral axis shifting towards top flange from the central axis by distance AH, which where the coefficient A is equal to sigma 1 by 2 into sigma 1. So there is a shifting of the neutral axis. Okay. Now, same all diagrams are superimposed together, and with the help of geometry, we are able to generate the possible cases. These are the stresses because with this figure, the stresses in top and bottom fibers, and we are with the help of the similarity of the triangles, we are generating a case of finding out the possible ways of the generation of compression and tension in the member in terms of the height alpha h. Alpha is this point where this diagram is finally coming, sigma TB and sigma BB, sigma top and sigma bottom bending. This particular height we are coming alpha h. In terms of alpha is coefficient, h is the height of the member. There are 5 possibilities. The different stage of stress in the bottom flange with respect to alpha R now. Different stage of stresses in the bottom flange with respect to alpha H. Because what we are worried that it should not happen, that total compression is generated. Total compression. There has to be tension. So that's the reason we are pointing out the various possibility. When alpha is less than 0.5, there is a tension. When alpha is equal to 0.5, bottom stress is 0. So that diagram becomes 0 at bottom and maximum at top. And when alpha is between 0.5 to 0.5 plus A, what is A? A is mentioned here. A is the coefficient here. A we calculate in this figure. A, sigma 1 by sigma 1 by 2 into sigma 2. So we get here the compressive stress appears, and when alpha is 1, total compression. When alpha is 0.5 plus into 1 plus alpha R divided by sigma naught, total compression. So however, there will not be any 6th stage as the stresses in the bottom quarter exceed the allowed design stress. So therefore, these are the possibility cases. So we have to work out the optimization of cross section and which we did. Belena has given a various different formulas for optimization or costing, because what happens if I can go again back to this figure, if this is symmetrical, you'll find that the bottom flange is unutilized. And one very important thing as per the steel design concern, there has to be evenly distributed stresses across the cross section. There are two legs. On one leg, you have large force, and another leg, they have less force. There is a disbalance in the body. So what we want, the stresses in the top and bottom fibers, because we are in the linear stress distribution. We are not in the rectangular stress distribution as far as the plastic theory or the Lipstadt theory concerned. So what we want, the stresses on top fiber should be more or less equal to, not exactly equal to, more or less equal to the stresses in bottom fiber. So if this is there, so what will happen? The stresses here will be very less, but the capacity is more. Okay, so thereby this distribution of stresses has to be done based on this geometrical distribution. Now, what should be the maximum possible pre-stress force? What should be the maximum possible pre-stress force? This is based on the no load condition. That is the beam which is initially prepared, stressed. Means bar has given me tension. So P by A plus P upon ZB is equal to R. R is the final stress which is going to come. Final stress will be nothing but equal to permissible bending stress in compression, which should be less than or equal to 0.66 times Fy if I talk about 84 code. Okay, so P is equal to this again simplified, and by multiplying a coefficient of buckling. Belena has given one coefficient of buckling that you should reduce the R by phi to take care of the variation in the design strength of the material. So therefore, R A phi ZB upon ZB plus EA. So this is what the maximum force you can apply. It's not necessarily mandatory that you should apply all time maximum force. You can control. Here you can control this force because it's a totally exposed, not in like a pre-stressed concrete. Once you did pre-stressing and you cut a wire and do the grouting in the conduits, sheathing, that is bonded. It is an unbonded tendon. Unbonded tendon, if you just keep wire for a particular length, so that you can again release it, and again you can again increase the force. So we can do sequential pre-stressing also here. So therefore, that is the maximum possible force we can calculate with the help of this formula. Now there is one more force which generate because of its own. That also generate in pre-stressed concrete, but the percentage of generation in pre-stressed concrete is very, very minimal, 0.00. I don't know what is the exact value. I discussed with one of the person who's expert in doing the bridge design in pre-stress. He said that this is very, very, it may be 0.001%. But I'm not sure whatever I'm putting, I'm not sure about that value. But here, again coming here, when this beam deflects because of loading, this wire elongates. So PL upon A, delta is going to PL upon A. So that delta, PL, that P is nothing but a self-pre-stretching force. After pre-stretching the plate girder, transverse load is applied. Pre-stretching force increases because of further stretching of the wire. Wire stretched. And that P is known as self-stretching force. And this self-stretching force can be found out by using virtual method. There are some mathematical equations. I'm not going to much detail of this. This will be taught sometimes if you all people allow me to have a classroom teaching, wherein we can go with mathematical calculations on these things. But I am showing you the process of how it has been calculated. This self-pressing force is a dynamic phenomenon. Dynamic means the load is there, it works. If the load is there, it is gone. it is vanish, which has been calculated with the help of the component of displacement of the tendons, and which comes out to be equation of these equations. P is equal to delta 1 P upon delta 1. Well, delta 1 P are the displacement due to external force and the unit force respectively. And here M is a main component of deciding the PS. So M, if the loading in the throughout the life of the structures remains same, then PS will remain constant. If the loading is variable, it changes from time to time. Time to time it changes, time to time it changes. Then this M will change. So what is to be done? You have to take a judgment. You have to find out this value of M in such a way that the largest force which is going to develop in throughout its life. And then we calculate. So therefore, we calculate the PS based on the these particular equations. The derivation we can draw very well. I have a derivation which we can draw it with complete calculations, and finally we can calculate the PS for the depending upon the bending moment considered, and the functions. Therefore this PS is a function of eccentricity, characteristic of material, and load condition. This eccentricity E, yes, because E plays a role for deflection. Characteristics of material, yes. If you go through 1343 or 6066 or the code for these all hardened wires or the prestressed material or tender, the value of E is slightly lesser than the value of E of a structural steel. So that also plays the role. And then loading condition. Let's see. Now I see that this is what the various bending diagrams which was useful for determining the self-lifting force. Now, based on these previous calculations, we can very well decide what should be the length of a tendon depending upon the alpha, the stress ratio, a coefficient. Sorry, not stress ratio, coefficient. So that what should be this LT? What should be this LT? Because that depends upon this alpha, which we calculate here. Yes, we calculate here. Alpha. So this alpha will decide you the length of the tendon. What should be the length of the tendon? Arbitrarily, you cannot put anywhere. But arbitrarily, I can say that 0.67 to 0.775 of L, if that will be for a simply supported beam. But exactly we can work with this particular equation. Now, this is what the initial preparation of the forces and distribution of the cross section. Now coming to the behavior. The tendon here in the behavior of the plate girder, the tendon is located on the tension side of the plate girder, so that tensile stresses in the tendon are balanced by compressive stress in the plate girder. An ideal stress distribution in which top and bottom fibers are equal, that we can find out. If the plate girder is designed as symmetrical, as I told you, the bottom chord is not utilized, and therefore we need to have designed the unsymmetrical section, or I can say use the word monosymmetrical. Monosymmetrical means one axis is symmetrical, another is unsymmetrical. So we are taking monosymmetrical on major axis, not on the minor axis. So coming to this distribution. So consider unsymmetrical steel plate girder subjected to initial load of Q per unit run, a constant force is applied at E from the drill axis, and we will see the behavior now. This is what the case. Just look into all. So this wire LT between these 2 points of stressing, and this is the UDL. Now, I will discuss that point also, but this is the most vulnerable point. Most vulnerable point of this particular beam is these junctions. We have to be very careful because here there is a large stress concentration and transfer of a force. So it has to be designed very carefully and properly. Okay, so coming to our main discussion now. Since I'm talking in between also so many things, so therefore sometimes it may change our the particular version. Oh. Now, due to pre-stressing, the compression, full compression on the cross section, and the bending tension at top, bending compression at bottom. Of course, one diagram is missing here, which is merged with the imposed load, which includes the self-weight also, which includes the self-weight also. Okay. Then, due to self-stressing, again compression increases, again the bending tension at top, bending compression at bottom, and finally the stress distribution here. Final stress distribution. So this is what the total status. The neutral axis, which was here at final stage, shifted to this point. So this the things which I just told you in the bullet point is written here. Now consider the case. Consider a case. We are considering a case of a plate girder under no external load condition. And no external load. There is no external load is coming. And then this case, even also I'm not considering just own weight. And therefore PS, that is self-stressing, is 0. Whereas corresponding movement is 0, and I is equal to AR square. That is R is equal to under root I by A. So which is being simplified as I is equal to AR square. So I wrote equation P by A minus M by Z for top fiber and P by Z for P by A plus M by Z for bottom fiber. There is a simplifying way. There is a one term E Y upon R square. If it is less than 1, then stress and on bending stress on top fiber will be compressive. This is already compressive, but this will be compressive. So what is the requirement? That in that case, the prestress force is detrimental, then helpful. It's not helpful. So what is important? Important that EY upon R square should not be less than 1. EY upon R square should not be less than 1. Here I am neglected the effect of external force and self-stressing. So what we should always, these are the silent points from where you can start to formalize the sections. Now coming to the deflection. So this is what the first part of the stress level, because in 84 code, we talk about the stress level, which should be less than permissible stress level. And then we talk about the deflection. So there are two deflections. One deflection is because of the pre-stressing, which calculate based on the moment diagram. And second, because of the working load. So net deflection will be equal to delta, which is equal to delta 1 minus delta 2. So what will happen now? At 0 line, first is go up, then come back to 0 line, and then go down. Right? So in all way, this our pre-stressed beam becomes a beam column. It becomes a beam column. So therefore, theory of beam column is applicable. Theory of beam column applicable. This can be divided into 2 parts. Theory of beam column. Those are PG students and PhD students. They can see the book of stability by any good author, Timoshenko. There are 2 cases. A beam subjected to 2 uniform movement and axial force. Case 1. Case 2. A beam subjected to UDL plus axial force. So there are 2 cases which is clubbed together. So this deflection now, based on beam column theory, can be found out. Delta is equal to m naught L square 5 times mu into 8 over EI. This is what I brought it from the Timoshenko book of beam column theory. And we can calculate the deflection. Now I compare two deflection curve of unsymmetrical eye section with one for prestress, another for unprestressed. Two deflection curve are shown, one for the prestressed case, another for the unprestressed. Origin for the deflection was chosen as a horizontal for unloaded and unprestressed stage. Using this plane of reference, prestressed deformation shown as a 0.4 on the figure 4. This is figure 4. Both the cases have elastic stiffness. Thus, two curves are parallel in elastic range. Prestressed case will exhibit a higher yield load value, but the ratio of ultimate loads between these two will not be as great as ratio of yield load. These two ratios depends upon geometry of the cross section of the beam, sensitivity, and value of prestressed force. You see that this is what the graph. This is the graph. So upward deflection due to prestress, and its behavior is shown with both the conditions. Yes, again the assumption number 5 is valid for this case. Now, every member there are some secondary effects. These secondary effects will create the secondary stresses in the member. So we have to check for the secondary stress with measuring the eccentricity, that eccentricity which increases because of the additional movement which develops, and the secondary effects are taken into consideration, which has to be worked out by these two equations. Then we have to work out about the lateral stability of the beam. That lateral stability is equal to m max equal to m naught sec u sec mu, and which is to be calculated, which to be worked out with. This is based on our equation of stability with these equations. No, okay. Now shear at all is as per the current condition, in elastic condition, shear is nothing but the shear stress tau average equal to 0.4 times Fy, and stress is equal to shear force divided by the wave area, which should be less than 0.4 times Fy. Nothing more about this. Reason being, we have to consider the flexibility of this K is equal to HYTW. If at all it exceeds the value, may add to stiffness, and this 0.4 Fy may reduce to some lower value. Being a beam column, interaction check is necessary. So we calculate this interaction between the axial stress ratio versus bending stress ratio, and it should be less than 1. It should be less than 1. And also the equivalent stresses, which is based on the bending stress actual and shear stress actual. So that equivalent stress also can be. These two are as per the clause of 7.11 of the 84 code. So the summary of this, now we'll discuss. Summary of this we'll discuss. What first we want, eccentricity Ey upon r square h should r square x should be greater than 1. Greater the value of E by h, greater the efficiency obtained by the prestressing. Okay, efficiency of the cross section explained in terms of rx square by h square. Okay, optimum value of r square by h square for I beam is taken as 0.165. Then unsymmetrical parameter, that is ratio of the centroid, is 1.5 to 1.7. Ratio of span length to beam length. L by H controlled largely by limiting the value to 20. So secondary stress can be neglected. And the initial stress ratio of FB upon Fi has to be taken as 1. So in total, for unsymmetrical parameter, Yb upon Yt should be between 1.5 to 1.7. K H by Tw should be kept as 85 so that no steepness are required. Parameter casting distribution material, that ratio of M, which is equal to AW upon A is the area of web. Upon A should be 0.5 to 0.66, and area beam should be calculated. A is equal to cube root of M square upon C square R square into K. Okay. Where depth of beam should be equal to under root K into AM. And accordingly, the area of flanges also be calculated. The value of C is 0.344 to 0.37. Now, this is worked out by the Belena with the different combinations. So he has suggested that C should be taken 0.34 to 0.37 and R should be equal to 0.66 times Fy. So a tentative cross section we obtain from here. Then we get tentative cross section of the beam with M equal to AW 55% to 60% of area should be given to web. And then we can plan a section to check the behavior of stresses and the depression. So this is what the summary. Numerical, likewise, have a normal book. Of course, this numerical is not at all to be constructed, beam which is constructed anywhere or not. It is a numerical we have just attempted. And we have worked out based on this summary which I mentioned just now here. Wherein the plate girder of 8 meter beam with load of WL by 8, moment we calculated, section area we calculated, then moment of inertia, then section modulus, then pre-stress force as per the formula which is mentioned earlier, and then pre-stressing force we calculated, then area of tendon we find out, then stresses we have worked out, and then stresses under load, that also we checked, shear also we checked, and stress in tension also we have checked, and deflections we work out, and stability also we checked with this equation, and interaction we work out. And simple numerical we have worked it, and this which is helpful in getting the validity of the theory which is been developed and given by the book. And we did in the research program, that also is validated by using this example. One more simple example, the deck girder of a meter gauge sections we have just taken, and under which the dead load, live load, and impact load be taken as total load, and which is been solved for the as a pre-stressed steel beam as a beam column. This is a section we adopted for the pre-stressed beam with the tendon area 175 mm square, which is modeled in SAP with P and E and M like this. This is the model of the beam column in SAP. This is what the deflected shape of in the pre-stressed stage, and this is the loading stage that we have just a new academic study we can calculate it, and then we check the result, analytical result and the FM results. Okay. Now coming to the plastic limit and behavior of steel. I'll just take a 2-minute break. A 2-minute break. Then we'll continue of the plastic limits state and behavior state. Yeah. So we'll continue the plastic limit state behavior of the plate girder. Now here, the assumptions are important. Two color lines on my screen is coming. I don't know why. These are the assumptions of plastic theory, which are remain valid also in limit state design. The plane sections remain plane, linearity of the strain diagram. Sections divided into equal parts. That's the reason we are calculating now is not stress capacity. We are calculating the section capacity. And there is one very important assumption that there is no actual load, which is while doing the plastic analysis, we assume that, but there is actual force. So there is an effect of actual force on plastic moment or MD, which we calculate in case of the pre-stressed steel beam. So effect of actual force and the shear stress should be less than V should be less than 0.6 times VD has to be checked while doing the analysis of this particular pre-stressed beam. There is also the redistribution of moment, shifting of neutral axis to plastic neutral axis, and one more thing. If I calculate the redundancy of the beam, which is for a simply supported beam, R is equal to 2. Sorry, R is equal to 0. And number of hinges required for collapse will be 1. And possible hinges will be 3. So mechanism will be not 1. There will be 2 mechanisms for the collapse. So collapse stages will be changed. So these are all factors has to be considered while doing the design of pre-stressed beam with the limit state. Of course, the study is not totally complete. We have not reached to the final procedure, but we are nearby to that procedure, and whatever part has been completed, which I am presenting here. Right. Now, the this is a table 4 of 800. So while calculating strength, we have to take care of the leading load and the accompanying load. The leading and accompanying decision has to be taken. The magnitude of the pre-stress force, which creates a moment, and the moment which is created by the external force. So therefore, if there is any change, it may be a vice versa. Right? So leading and accompanying load changes has to be leading accompanying factor has to be considered while deciding the cross section. That is point number 1. Then, of course, the safety factor has to be according to this our table 5, which we'll consider same. Then deflection limits, as it was 325 constantly in the 84 code, but now it is changing according to span to span. But if you take relative span, relative deflection, the beam will face from 0 to minus and minus to 0 and again plus. So total deflection may be exceed more than this, means from hogging to sagging. Total deflection may be greater than this deflection. So these are some salient points to be decided to be before going for the final conclusion on this. Okay, then the table, this table of maximum cylinder ratio. that because we are introducing compression, so the KL/Y ratio of the member should not exceed 180. That point has to be taken into consideration. And if required, the bottom flange under pre-stressing with no load condition, there is a compression created. So it may happen that the compression flange of beam should have the ratio of KL/R as 300. So this has also to be considered. Then classifications as probably Professor Subramaniam also is in the as a participant. He is there. So I referred this figure from his book, and we have to take plastic or compact or semi-compact sections, and then according to decide on things. Then that the limit of ratio. Now here, the R1 R2 also is a challenge, because under pre-stress condition, the R1 R2, the nature of stresses may change. So decision on R1 R2 may be taken. In that case, you may refer also the British code, which will help us to take the decision on R1 R2. Now coming to the behavior, elastic behavior, already we have seen. That is stage number 1. Whenever if I go on the plastic bending of the beam, so where the first case, the beam is in the elastic condition, the stresses are well below the yield stress, and then again the load increases, the yielding starts at top and bottom fibers, and thereafter the elastoplastic stage starts. So I'll go to the elastoplastic stage now. So that is the behavior under elastic condition. The stresses condition in the elastic range may be conveniently subdivided into 4 stages. One, beginning of fiber yielding. Extreme stress either the top and bottom fiber reaches to yield. This is limiting stage of elastic range or behavior beyond which the elastic deformation just begin. That is what is stage number 2. I can say that. Then elastoplastic stage, the plastic deformation starts penetrating the cross section, which increases in the self-stressing force. Yes. Here the deflation increases. If you go by the referring the book by Steel Skeleton by Baker, and there are 2 methods, step-by-step method for plastic analysis, and correspondingly if you plot the movement curvature relation, and correspondingly you calculate the deflection. So that will helpful to analyze the elastoplastic condition. The plastic deformation starts penetrating the cross section with increasing the self-stressing force. The self-stressing force increases at a greater rate than the elastic range, because when it is in the elastic range, the deflection increases, not much increasing the stress. The plastic range material may be put into advantage one of the following case. The ductility is the unique property of steel, advantageous in the plastic range of the beam material, and the plastic range may be then put to good advantage in one of the 2 cases. When the plastic deformation develops in the course of loading, and when plastic deformation develops in the course of pre-stressing. There are 2 possible cases. So in elastic plastic case, the diagram stress depends the maximum ordinate equal to design strength of the outer fiber and the bottom fiber, and pre-stressing force active in the tender. So this is what the stage of elastic behavior. This is elastic behavior, then elastoplastic behavior. Then full plastic stage. Okay, if the stress in the tendon is still below the design resistance than the plastic range, that does not signify that the beam has been stressed to the capacity. In the second case, plastic deformation are developed in the pre-stressing stage itself. We can show in figure. The beam is in the elastic range of behavior from the beginning of the pre-stressing to attainment of the yield stress in the bottom card. So you can see that here. Elastoplastic behavior, that in the bottom card, the stresses are fully reached, and elastoplastic behavior, it is reached, and then the full plasticization. And then finally, the full plastic stage develops. So what we are interested in forming the plastic hinge under the load. At this end, maximum bending moment because of the bending moment which is developed because of the load, not because of the pre-stressing. Okay. So the plastic movement capacity of the section now can be calculated as MP is equal to Z into sigma Y plus PE minus sigma Y TW upon into A minus H1 whole square, where A is equal to H1 plus P upon 2 times sigma by T. So here the plastic mold capacity has been calculated by using the equations of considering the effect of axial force. And the section to be checked for plastic interaction using 800 formulas PF upon PY plus MPC upon 1.1 MP should be less than 1. SP6, if you refer SP6, P upon P less than 0.15 effect of axial force to be neglected. But how much is applicable? Unless until we solve some more examples, more actual cases, then we can see. So one simple limited example we work out for this section, which is plastic, and these are the geometrical properties. These are the stresses and forces in the plastic regions, and these are stress diagram, and we achieved it. Now coming to the third part. Yes, before I go for the third part. So here, the study which is remaining, which I am ready to continue, provided I should get some PG students. I requested my student whether I can be able to get some students to work on this. That the shear strength in the post-buckling behavior and the performance of the pre-stressed beam during the collapse. So these are two more studies are remaining, which can be continued so that we can come up with a one complete process of design of the pre-stressed steel beam with a manual of the design with limit state method. Of course, some literature paper available is also available, so that also can be seen. Stability is a big challenge here, and stability is being studied one in the MTech program, 2 in MTech program, and 1 in PhD. So the first stability was this torsional buckling study first carried out. That the plate girder pre-stress eccentrically behave as a beam column. So it's subjected to axial force, bending moment, and shear. So this concept was studied and given by the Blasov. That's why that circle is called as Blasov circle of stability. So for that, what is been considered that we are simply supported beam in which the depth of neutral axis is 2.1 and the depth of wave taken as span by 10 subjected to dead load plus pre-stressing, dead load plus live load plus pre-stressing plus self-stressing. And the critical axial force NCR is calculated by using this equation, which is given by Blasov, and he has given a circle, which is called as Blasov circle of stability. I have not included here derivation, but Blasov circle of stability is to be worked out based on the torsional behavior of the beam. And that what is the outcome? That the tendon is located outside the circle of stability, buckling is impossible. Since the critical force in the tendon which is required for this girder to buckle is not tensile but compressive. So we should work out the E and we could calculate this particular phenomenon. That is the first torsional buckling equations. Okay. Then lateral torsional buckling equation. So far, in the previous case, we have not talked about the lateral torsional buckling, but one study is carried out in lateral torsional buckling, behavior of the laterally unsupported pre-stressed steel beam with monosymmetric cross section with torsional restraint under the different load conditions. Effect of governing parameters such as span length, magnitude of pre-stressing force, tendon sensitivity of the buckling behavior of the stress I-beam, effect of self-stressing force is affecting the response of pre-stress I-beam. So these are the initial conditions are considered. So what we consider a monosymmetrical I section. Degree of monosymmetry is decided based on the moment of inertia of the flanges. Top flange divided by total moment of all the flanges. Okay, then T by TW taken as 45. And one particular beam of this dimension has been considered. for span 6 meter, 12 meter, 18 meter, 24 meter. For prestressing 400, 300 and 500 with eccentricity 1.1 h and 1.2 h. Okay, so these are being considered, and the analysis we carried out using the ANSYS software, and the different graphs between displacement versus movement has been drawn for the 1.1 and 1.2 eccentricity ratios with D by W ratio 45 for 6 meter span, for 12 meter span. This is what a typical buccal shape of the beam with P is equal to 300. Here also, these three lines are for 300, 300 and 500. This is for typical 300 square case. Then again for 18 meter with 1.1, 1.2, for 24 meter, again 1.1, 1.2, and the strength has been compared for these three, for compared by the strength of the member for the depth various depth as 1.1, 1.2, and again for these 12 meter, 6 meter, 6 meter, 12, 12 meter, 18 meter, and 24 meter. So 24 meters are not satisfactory, doesn't give satisfactory results, whereas up to 18 meter, yes. The smaller span give satisfaction, but higher span doesn't give satisfaction. And what is we just draw a conclusion. Prestressing the monosymmetric section with smaller D by TW ratio for increasing the buckling strength of the beam is effective over smaller to medium range. Strength is decreased for such section for long span. Hence, monosymmetric section with D by TW ratio of 45 can be effectively prestressed to gain a buckling strength of smaller to medium span. But here we have restricted this value. We have put a constraint on here, because otherwise the whatever one problem becomes a undefined and not able to get a conclusion on that, but not helpful for large span 24 meter. Okay. Then effect of load height. Now effect of load height. Load applied at top flange, shear center, load at the centroid, load at the bottom flange. Because beam to beam connections where load transfer is not been known, so which has been studied for using SAP, and the span varying from 10 to 24, and load applied at different places, different locations, which is shown in this figure. And the stresses are calculated for from 10 meter to 24 meter span in the bottom flange, in the top flange, with displacement also. And this observation what say that no effect on either the maximum displacement or maximum bottom stress. Slight difference in the maximum stress in the top in order of 2%. So not much of more difference, because of the pre-stressing, the member is more stable. Now coming to the examples, application part. Now coming to application part. We have did lot of testing in the lab. When I did my own PhD, I tested portal frame. My another student tested beam. My one student tested truss. So whatever the possible photographs which are available, I have just collected, gathered, and then I'm presenting here. First is the beam. So beam profile, five profiles are considered. straight tendon over full length, straight tendon over partial length span, V-shaped tendon, cord-shaped tendon, and trapezoidal shaped tendons. This is a straight tendon partial length. This is V shape. This is trapezoidal shape. This is cord shape. You can see the model. You can see the wire which is connected here between these 2 points. Right? This is V shape. This is girdle 3, girdle here. This is 4. So this is the jack by which we are doing the pre-stressing. Pre-stress jack. We are pre-stressing the beam. And then we are testing them. And we are measuring the deflections. Central point load, and we are measuring the deflections. This is UDL. This UDL transfer through this roller which put it here. And deflection measure at the bottom with the help of the dial gauges. And you can see this is wire. And these are the comparative statement results. Maximum load carrying capacity, then pre-stress force, eccentricity, and percentage increase the load carrying capacity. And we have generated the equation of forces. Equation of forces of self-stressing force for the point loaded center and UDL. Okay, then one analytical study in one of the MTech project, of which the paper is published in the Structuring Journal of ACRC, Madras, wherein the one continuous beam has been solved. This is a continuous beam. You can see the wire here in sagging zone and wire here in the hogging zone. We can have wire as a continuous one. Of course, here we have to put some rollers, some arrangement, we have to make it arrangement for this transfer. And the sections analytically be solved, and the sections are provided here. This is the continuous beam. This paper is available, very much available paper. And the percentage saving for the continuous beam. Now coming to this portal frame. Now, the previous photographs of beams which we have shown, all the dimensions of the beam span has been decided based on the availability of the space in laboratory for testing and loading capacity. There is no relevancy of any prototype available from where we can scale down the model. And this is based on the space available, loading system available, and based on that we have decided the cross section and we have tested it. But here in this portal frame, this is my own PhD, 1984 to 1990. This is one part of the structure of thermal power station, where the span is 39 meters, height is 29 meter, length is 200 meter. It has a 100-ton capacity crane. Very heavy crane structures. So that was totally designed with the plate girder And we have attempted to design with using the open web sections with prestressing and column with hollow sections. So we have used these tendons and we did the model testing. So this is the drawing which finally we have designed in the project with open web beam and the hollow sections. And this is the model we prepared. So here we did model analysis based on the material available, size available, space available, and loading what we can upload, because we cannot scale the loading. So here in this model we prepared with the open web section, 4 angles with lacing of 6 bar with 2 brackets. 2 brackets have been welded here, and a 4 wire been provided for the prestress wire, which is a sensitivity at a sensitivity. And this you can see in another picture. You can see the very close up of the beam where the wire is been prestressed, and you can see during prestressing the member is been deflated upward. So here in this beams which we are taught, it's simply supported. But when this frame we did, this is what the hogging moment. So there is a distribution of moment, internal distribution of the moment at the joint. So there is we get advantage also in column. So portal frames are advantageous. Get a reduction in movement in the column also. Then this is one Prestressed instrument wherein I applied the load of 1400 kg for 4 wire, which we can measure. It is to be hanged on the wire and is to be screw tight, and we can get it. Now, that time I got this wire from the pole factory, because pole factories are of electricity board. I was in electricity board. So pole factories, they are preparing the poles, prestressed concrete poles. So from there, I got a sample of a piece of wire and also this instrument. So which is helped me in performing the experiment. Then we have 6 channel indicator to measure the strain. This is what we had tested in 1988. 88. And this was a 60 design with the help of this jack. A upward load is given so that the load which is coming here, the bracket, because of the crane, which has been simulated. These are 2 fulcrum we made it with ratio of 1:3, and it is been pushed. So the wire is hanged. So this wire, you can see this wire, this wire. This is the strand which is pulling the force, and this is raising like this. So this help us in generating the force. So we have a very little resources that time, and anyhow we have managed to test the structure. Now it has become very easy to test. If I to do this one now, this is what the loading we did it. Front line cladding loading, then top loading we are hanged with the nylon ropes. So this is what we did the testing of these portal frames, and we compared the result of stresses and the deflection. Then one project of testing, we did it for the shield truss. Now, in the forms and shapes, I show you these sections for the tension member. But procedure I have told you. So procedure I have just noted here. If to find a force in all member due to dead load or live load, member which are in tension are to be prestressed, and prestressing capacity has 50% of loading capacity in compression. That means that member initially before coming to load to be checked as a compression. Then find the actual prestress force and calculate net force and adopt a section. So this is what the one truss we analyzed. This is the truss also part of the conveyor belt structures of the power station for the all the forces, dead load, live load, and the prestress force. This dead load, live, prestress force, and then it tested in lab. This is the under no load condition. There is no external load, only the pre-stress and the condition we will find out deflection first. You can see deflection, the pre-stress curve, and this is what the thrust. This down, we have hang the weight. You hang the weight. So based on this all model analysis, I wrote down one guidelines how to prepare a lab model and how to do the model analysis for such type of structures. You can see the testing of different sections with adding the weights. This is another truss which is having 1, 2, 3, 4 cables which has been tested here with 2-point load. Now, one example we solved of the arch with the different profiles and work out the economy. Then one example of one bridge girder, which open wave beam with 6 number of cables as an analytical study. And then we work out one example of how to rehabilitate these structures. So this capacity of this bridge to be increased. So this is what the we added 2 angles and 1 strand here, 7-ply 15.2 strand, which will help us in increasing the capacity. And we have one loading frame of which we have to enhance the capacity. So we have did the pre-stressing of this frame with four wires, and capacity has been enhanced of this frame. Okay, so these are all the cases I have presented here. There are more cases available with me, but looking to the time constraint and the at a glance to show everything, I have not added some other things. Okay, so this is what about the application. No, what are the various methods? No, there are no known methods. Some of the known methods mentioned here, but nowadays we have been have a developed technology. We can have a various way of stressing the members. We can also get the new structures, as well also we can go for the rehabilitation of the structures by using this technique. So what in finally what we need? Basic structures, tendon of high stress, anchorage, saddle, diaphragms, and additional labor. We need additional labor after making the structures. So what are material now? Plain hard run steel wire of 1785. Cold hard intended wire confirmed to 606003. High tensile steel bars or uncoated stress relieved strand of 606006 or uncoated stress relieved low reluctance 7-ply strand confirming to 14268. So these are the pre-stress material. This is what is regular pre-stress material. Watch with the pre-stress concrete people they use. These methods I have mentioned, but I am not telling more about this. More advances are coming. I may have to modify this slide also. This is what the lab jack we have for pre-stressing in our B90. And these tendons about the pre-stress material, everybody knows about these tendons, these configurations. And these are anchorages, various types of anchorages. Now we can use all systems of anchorages, various systems. Somebody, I think so, put one question on chat box. Loss of pre-stress due to anchorage slip, loss of pre-stress due to friction, and relaxation loss. Question arises about the prevention of the pre-stress material. So we can have a sheathing arrangement so that it can pass through sheath, so that it's not visible. Nobody can hamper it on this way. That can be done. Grouting of the tension table can be done, but not desirable in case of the pre-stressed steel. There are some secondary effects buckling under pre-stressing. That is what during the pre-stressing process, erection at the time is some erection and erection stress added. Some local stresses at anchorages, and the study is pending. Again, one more study is pending, that is fatigue. Though Belena has given the procedure for calculation of fatigue load, but yes, more things are necessary. Some fatigue testing to be done on this point. These are some information I have about the structures which has been made in India. There may be more, but I am not much aware. I have only this much information, so which I placed it here. And at the last, somebody also put the name of the book. So book is the Beliana E. Prestressed Load Bearing Metal Structures. That is one book. And number of papers. And there is one more book. Praski MS, Prestressed Steel Bridges, Theory and Design, Van Non-Stand, Railroad, New York. So these are the two books we have referred, but we have referred mainly the book on Belinia. Others are the papers and our thesis, which already I given in the initial slides, which very much available with me. 30 number of MTech project and 3 PhD theses are very much available with me, and some papers which we have published. There's also some of the papers we have. Right. So this is from my side, and the last, I must thanks all of you. I must thanks INSDAG for inviting me this topic, because while retiring after that, I understand that this topic will remain in my Almira shelf. But the Manas Ghosh has requested me, and he has said that no, sir, let us take out all the things and let us make a presentation on this. So with his, I can say that with the request or with his pursuance, I have prepared a little bit with lot of, there may be a lot of errors, because very hurriedly in 10-15 days I have prepared it. There will be a lot of errors, lot of things are left out, and hope so that I am able to correct it, and the remaining study I am able to do it. That is that man proposes, God disposes. So with this all, thank you very much, and if have the questions, we can put it. There is a Professor Dr. Subramaniam has raised the hand, and he had some questions. Yeah, Professor. I think so. Mic is muted. Dr. Subramaniam, your mic is muted.
I don't have any. So I want to appreciate you for covering so much material in limited time.
Yeah.
Of course, I have heard about this pre-stressed steel structures. Of course, I have not worked on it, so I am very happy to note that you have worked on it. And incidentally, Professor M. Basole was my PhD external examiner.
Oh, so he's alive. He's 93 years old.
Oh, I see.
Yeah, I talked to him last week.
Oh, excellent.
Yeah.
So he came all the way from Nagpur to IIT Madras to conduct the exam.
Sir, I met you in the computer design consultant. Your office in Chennai.
Oh, okay.
And you organized one conference that also attended.
Okay, thank you. So you can send me your email ID so that I can contact you.
I'll send my email ID.
Okay.
True. I'll take your email ID from these INSDAG people.
Yeah, they don't.
Yeah, I'll take that. Thank you, sir. Thank you, sir, for attending this lecture.
You are welcome.
Sir, because I was thinking how much I should left out, because there's no place to left out, because I cannot do incomplete elastic theory. I cannot talk incomplete stability theory. So that's why number of slides becomes 185.
Yeah, correct.
But if I go very slow and with the complete details, it takes around 3 to 4 hours.
Yeah, that's what I told you in the beginning.
Yeah.
So you covered so much in a limited time.
Yeah. Thank you, sir. Thank you.
You're welcome.
Yeah, Siddharth, questions from
Yes,
chat
sir.
box.
Thank you very much, Professor Gupta, for such an insightful presentation. We shall now move to question and answer session. I request all the participants to post their question in the chat box. So I'll take, sir, few questions. Sir, first.
Siddharth, I have
Yes.
opened chat. I opened a chat box. I will read one by one and give the answer.
Yes, sir. Yes, sir. You may take, sir. Please, sir.
So why tendons at bottom? Because we want opposite stresses in the member. Ramakrishna asked me a question. Why tendon at bottom? Because we want opposite stress in the member. That's why bottom. If it is a cantilever, you can have a top. Then slide is moving. Yes, slide is moving. How determine the losses of pre-stress? That I told you at the end. Pre-stress losses. Then reference book, I told you Belena and the Troitsky. Yeah, can you idea about my economy? Economy is around 20 to 25% in trust bridges. Available codes for dinner pre-stress? No code. We have to use our technology only with available code of IS 800 and IRC 24. This Hemant has asked a question that excite example of actual one of the consultant of Nagpur who has rehabilitated one building in Mumbai, but I'm not able to get the details. I told him to give me photographs, but I don't know photograph available or not. But yes, there are some buildings which has been rehabilitated using the Prestressed steel. Can we add processing cable on both sides of the web? Yes, sure. And that is what necessary. Reason being, otherwise lateral instability. Sir, what amount of load should be tried and balanced? On the case-to-case basis. Case-to-case basis. Okay. Then what amount of load should be tried and balanced? Thank you for information session. Thank you for wonderful lecture. How can we pre-stress in continuous beam? In continuous beam, we can do pre-stressing in piecemeal basis. We can do piecemeal basis. First and what hogging say, first is hogging side, then is sagging. एक किसी ने पूछा है how has there been a study on blast loading on pre-stressed steel concrete composite cutter? No, I'm not aware. You have to check. So these are all the questions which I have answered here from the chat box, and that's all. If anybody has any question more, can be welcome. There are 3 more questions. Sir, I am ME observation student. Please suggest topic related to that. Yes. Write me mail. We can interact. This is Krunal. Krunal, you write a mail. You can take my email ID, and we can interact. I can give a topic. Sir, is the Raju Krishnan book enough? No. Raju Krishnan book is not for this pre-stressed steel. Can we build a pre-stressed steel tower, transmitter tower? Yes. There is one chapter. There is one chapter in Belena book. We have not talked about the compression member. We talk about tension member. He has suggested a tower with compression and the cable as a secondary member. So that's yes, we can do it. Or the thesis of your MTech is published. It's not published. It is a hard volume available with me. Only 13 are available. About 6. Not difficult to get our remaining 6. Then my email ID. I think so. My email ID will be how I can put it here. There is any way to write? I don't know how to write.
We may share with the participants, sir.
Okay. I am very happy to see my one student from Australia. She has attended the course. She did PhD under me and now she settled at Australia. I saw her name here while attending the course. Ritija, thank you very much. There's one more question.
Thank you, sir. It was a very good presentation.
Achha, use chat box. Okay. He said me to write my email ID and use chat box. Yes. I put it in chat box, my email ID. Anything else? Any more questions?
Sir, if any participant is having additional question, they may mail us at seminars@insdag.com.
Yes.
Thank you very much, sir, for patiently answering all the questions and sharing your valuable insight. We sincerely appreciate your time and your excellent presentation. It has been highly informative and enriching session for all of us. Before we come to end of today's webinar, I would like to invite my colleague, Mr. Munib Mehraj, who will be talking about our activities and about the upcoming training seminars.
Okay. Hi everyone. Am I audible to all? Hello, am I audible?
Yeah.
First of all, thank you so much, Dr. Gupta. It was a pleasure to hear you and on such a niche topic. And I hope all the participants would find value. And while we were here, while you were seeing participants here, we were also live streaming on YouTube. So a lot of participants also joined from YouTube as well, which is a very good initiative that we have taken in the recent times. But overall, sir, the presentation was really insightful and we all thoroughly enjoyed through it. Participants, I'll just take 2 minutes of your time before we can close this session. I'll just, sir, can I share my screen, sir? Dr.
But
Gupta?
there are some two more questions.
Yes, sir. Please, sir. You can
I
first
think
take
there
them.
are some two more questions. No.
Please.
It's over. Nothing. Nobody. You can share. I will stop my sharing.
Okay,
Okay.
sir.
Now you can start. You can start.
I'll start. I hope my screen is visible to all. Participants, is my screen visible?
Yes, visible now.
Yes. Visible.
Thank you for the confirmation, sir. So I'll just give you a brief about INSDAG and our training programs. Although our Director General gave a brief about what we do. So if any of you doesn't know, because a lot of new participants had joined for this program, all the major steel producers and the ministry has founded us in the year 1996, and we started functioning in 1999. So we have a long history. And apart from these steel players, we are also interacting with the user industry. There is L&T, APL Apollo, Kirby. There are some institutes, ISRO, IIT Bombay, CBRI. These are all associated with us through various initiatives. We are involved in many activities, in trainings, in structures, in codes and standards. We are involved in ministry. We also do some consultancy jobs. We are also involved in some green building certifications as well, and we are also involved in customized training solutions for corporates. So I'll just take you through some of our training programs that we're going to do in the next couple of months. All the details of these programs you can find on our website, and you can always reach out to us at seminars@insdag.com. I'll just quickly take you through. The first program that we are doing is on fundamentals of cold form steel design. Now, this is a very important and on a very niche topic that we are doing, and we'll have faculty from IIT Hyderabad. This will be a 2-day course, all online, and participants, if you find value, you can enroll for this program. Then we will have a program on steel concrete composite structures. Again, a very niche topic, a very important topic that we are doing in association with CSI. Now, CSI is the same institute that is the reseller of ETAPs. They actually make ETAPs. So we are associated with them, and they'll also have a session, and we have a very good lineup for this course as well. Then we have a training program on connection design, again a very niche topic where we have joined hands with Idea Statica. And this again, participants, if you find value, you can join this program as well. Then we have an offline program. Now, this is something which many of you, if you are in Calcutta, around Calcutta, this is in our office. We are doing one on quality essentials in steel structure fabrication. This will be in-house at INSDAG's office, and it will be one of its kind program that we are doing for the first time. Now, all these programs you can find on the website, and will share you the details on your mail as well after this program. But before we go, I just want you to know, if you register, you can register for these programs one by one also. But if you want, you can take bundle registrations where you can take registrations for 4 programs, 5 programs, 6 programs, 7 programs. And based on that, you will get discounts. And also, if you are a member in any way, you are a light member, annual member, your institution is a member of INSDAG, you will be able to get 30% additional discounts. And I think that is it. That is most of what our activities. And I just wanted to take you through our training calendar, because we are doing knowledge dissemination sessions across various platforms. So if any of you is interested, we'll be sending you a mail. But if you're interested in any other program as well, do write to us, and we'll be more than happy to include a session on that as well. I think that would be it from my side, everyone. Professor Gupta, any additional point we missed out on?
Nothing, I think so. The questions which have been posted in the chat box already answered.
Yes, sir. Yes, sir. Yes, sir. Sir, if there are any additional questions, we'll write back to your email, sir.
Yeah, sure.
I think, sir, Dr. Subramanian, sir's hand is, sir.
It is on, but already I talked to him.
Okay, sir. I think, sir, then we can close the program with your permission. Sir is here, sir.
Yeah.
Dr. Subramanian, any additional questions, sir? Sir, anything, sir? Sir, did we miss anything, sir, Dr. Subramanian, sir? I can't hear. Maybe. Yes, sir.
No additional questions.
Thank you, sir. Thank you so much, sir, for joining.
You are welcome.
Professor Gupta, with your permission, can we?
We can. Yes, surely. Thank you very much.
Thank you so much, sir. Thank you so much.
So I will leave the meeting, huh?
Yes, sir.